So, next is the capacitance of a single phase line, right. Now, look at this figure, you have two conductors. Listen one thing, for the capacitance case there is no question of R dash, right, like inductance. So, this should be in your mind. So, now you consider a single phase line, this is there are two conductors, this is Q1 and Q2, charge is Q1 Q2, and if Q1 is equal to Q, so positive charge, then Q2 will be your minus Q, right. So, later we will see. Now, the radius of this conductor is R1, right, and radius of this conductor is R2. We have to initially we have taken that it is your what you call radius of two conductors are different, and center to center distance is d, right, center to center, and of course, d is much larger than R1 and R2, right. So, this is single phase 2 wire line, right. So, conductor 1 carries a charge of Q1 coulomb, I told you, and per meter, and conductor 2 carries a charge of Q2 coulombs per meter, right. The field of the first conductor is disturbed due to the presence of the second conductor and the ground, right. So, basically if you take it, now we are considering single phase 2 wire line, naturally field of this one will be disturbed by this one as well as by the ground. Ground we will see later, right. So, distance between the conductor is d, and d is much greater than the radius of the two conductors R1 and R2, right. Also, the height of the conductor from the ground is much larger than d, because conductors are always above the ground, right. So, that height h is much greater than d, but when we will consider h, that we will see later, right. So, therefore, the effect of distortion is negligible and the charge is assumed to be uniformly distributed. So, we are assuming that the effect of distortion is negligible and the charge is assumed to be uniformly distributed, right. The potential difference V12 can be obtained in terms of Q1 and Q2 using equation 5. That general equation we have given, m is equal to 1 to n. So, the same equation from 1 to 2 we are using 1 upon 2 pi epsilon 0, two conductors are there, m is equal to 1 to 2, this is q m, this is ln d 2 m upon d 1 m, right, volt, right. So, this expression just now we given no this expression d I m upon d k m, right. So, I is equal to 2 and your k is equal to 1, right. So, therefore, it is m is equal to 1 to 2. Now, V12 is equal to 1 upon 2 pi epsilon 0, then Q1 ln d21 upon d11 plus Q2 ln d22 upon d12 volt. Now, since Q2 is equal to minus Q1 and d21 is equal to d12 d, actually two conductors are there, conductor 1 and conductor 2. So, that is why d21 and d12, that means this is here to here 1 to 2 1, basically this distance is d, but this is generalized formula, after that we are replacing this, right. So, d and d11 I told you that if I k is equal to m or I is equal to m, then dmm is equal to r. So, when d11 is equal to r1 and d22 is equal to r2, right. Therefore, V12 is equal to 1 upon 2 pi epsilon 0 q1 ln d upon r1 minus q1 ln r2 upon d, because q2 is equal to minus q1, that is why minus q1 ln r2 upon d volt, right. Therefore, V12 is equal to 2 q1 upon 2 pi epsilon 0 ln d your square root of r1 r2, because if you this is if you take q1 common and it will be basically plus ln d upon r2, because it is minus ln r2 upon d, it will be d upon r2. So, that you are after that you simplify this, it will be d 2 q1 upon 2 pi epsilon 0 ln d upon under root r2. I mean these things are simple, I am just for your clarification just writing one line. So, V12 is equal to your 1 upon 2 pi epsilon 0, then q1 ln d upon r1, right, and minus it is written q1 ln R2 upon d, right. Therefore, this is equal to 1 upon 2 pi epsilon 0, you take q1 common, right, and this one is ln d upon r1 plus ln then d upon r2, right. That is equal to q upon 2 pi epsilon 0, then ln d square upon r1 r2, right. This one you can write no q upon 2 pi epsilon 0 ln, right. Then you can write d root over r1 r2, right, this square, this is square is equal to 2 q1, it is q1 actually, it is no, you are putting your this thing, it is q1. So, it is q1, then 2 q1 upon 2 pi epsilon 0 ln d upon root over r1 r2, right. So, that is the simplification. So, that is why you are writing here that this one is your what you call 2 q1 upon 2 pi epsilon 0 ln d upon root over r1 r2 volt, right. That means, therefore, our objective is that you have to find out capacitance between the two lines C12. Therefore, the C12 is equal to, it is q1 upon q is equal to Cv in general. Therefore, C is equal to q by V. Therefore, C12 is equal to q1 upon V12 is equal to pi epsilon 0 upon ln, because this 2 will be cancelled, right, 2 will be cancelled. I did not make it here, but this 2 will be cancelled, right. So, therefore, C12 is equal to q1 upon V12 is equal to pi epsilon 0 upon ln d under root r1 r2 farad per meter. This is equation 7, right. Therefore, if both the conductors radius same, then r1 is equal to r2 is equal to r. Therefore, C12 is equal to pi epsilon 0 ln divided by ln d upon r farad per meter. This is equation 8, right. So, epsilon 0 you know 8.854 into 10 to the power minus 12 farad per meter, this is known, right, and this is your natural log, but you convert it to this log, right. So, this conversion is up to you, right. So, this simple thing you can do it. So, generally for all the numerical this that we will use log of this thing, right, not the natural log, right, because many things easy to remember. Therefore, C12 is equal to, if you simplify, it will be 0.0121 divided by log d upon r microfarad per kilometer, right. So, this is equation 9, right. So, this is the capacitance. So, this equation 9 actually it gives the line to line capacitance between the conductors, right. But for the purpose of transmission line modeling, it is convenient to define the capacitance between each conductor and a neutral as shown in figure 4. So, this is line to line your capacitance, but in between line 1 and 2 if you have a neutral, then you have to find out that capacitance from each conductor to neutral, that is C1n and C2n. So, that means, if you come to this first. So, when 1 to 2 this is the C12, that is whatever you got, whatever you have got, C12 is this one, right, equation 9. Now, if you have a neutral in between, this is the neutral n, right. So, this side 1 to n, this is the C1n and this is C2n, right, and these two are in series, right. This is conductor 1, this is conductor 2, right. Therefore, C1n is equal to C2n is equal to 2 C12, because they are in series. So, C1n is equal to C2n is equal to 2 C12. That means, C1n is equal to C2n is equal to this will be multiplied by 2, right. That means, it will be 0.0242 divided by log d by r microfarad per kilometer. This is equation 10, right. Now, the associate line charging current will be I c is equal to j omega C12 V12 ampere per kilometer, right. So, it will be, if you think like this, something like this, that if you try to find out the reactance, say x, I put x12, say x12, your what you this thing, your generally you know that x is equal to 1 upon omega c, right. Therefore, if I make it x 12 is omega by c 12, right. So, this is that reactance. Therefore, when you try to find out the charging current, say IC, right, is equal to in general I am putting. So, voltage is V 12 divided by your x 12 is equal to your omega c 12 into V 12, but as it is a capacitance, right. So, this your what you call, then you instead of magnitude here you put j, here you put j, therefore, it will be j, right. So, that is why this line charging current will be I c is equal to j omega c 12 into your V 12 ampere per kilometer, but if you take the magnitude, then j should not be there if the magnitude is taken, right. So, it is a leading current, right. So, that means this one more line I am writing for you, that means this one will be I charging current will be omega c 12 V 12 angle your 90 degree, because j is there. So, this ampere per a kilometer, right. Therefore, this is your general thing. Next is capacitance of a 3-phase transmission line, right. So, for transposition no need to explain here now, because already for inductance case we have explained that transposition of transmission line, right. So, you assume there your 3-phase transmission line, right, and this capacitance of 3-phase transmission line and lines are transposed. So, this is phase A, phase B, phase A, phase B and phase C, right. Distance between A to your C actually D31, that means DAC actually D31. I have not written it, but I am telling from my mouth. So, you will know it, right. Similarly, DAB actually is equal to D12, right, and similarly DBC actually D23 capital, right. So, not making it here, but at the time of derivation we will see. So, if you want you can make it, but DAB is equal to D12, DAC is equal to AB, BC, CA. So, DBC will be D23 and DCA will be D31, right. So, this is the line transpose. So, first section 1 it is ABC, next section it will be CAB, that is section 2, and third section it will be BCA, this is the third section. So, this already we have seen for the inductance, right. So, 3-phase transmission line, this is figure 5 fully transposed, but here I have written here D1 to DAB, D23 DBC and DCA is equal to D31. Now, for balanced 3-phase system QA plus QB plus QC is equal to 0, this is equation 12, right, like your current IA plus IB plus IC is equal to 0, right, assuming no neutral, right. So, next is we will apply the same formula, right. So, potential difference between phase A and B for the first transposition cycle, I mean for the first one, for the first transposition, that is section 1, section 2, section 3, first we will see the first one here, right. So, that means can be obtained by applying equation 5, the same equation again we will use the generalized equation. Therefore, VAB in bracket this I means it is not current, it is section 1, right. So, VAB bracket I means for this section 1, right, is equal to 1 upon 2 pi epsilon 0 QA ln D12 by R plus QB ln R D12 R by D12 plus QC ln D23 upon D31. This is equation 13, but same equation 5, the generalized equation we are applying. For inductance also for flux linkage we applied one generalized equation. For capacitance, for voltages also the same equation we are putting in this form, right, that means QA ln D12 upon R plus QB ln R D1 R by D12 plus QC ln, that means QC ln D23 by D31, that is QC ln D23 by D23 by D21, right, because you want V your AB, right, due to for the section 1. So, this is that configuration of section 1. This triangular configuration for this one and this one you can draw, right. For inductance case we have shown it, so no need, right. Therefore, your this one will be 1 upon 2 pi epsilon 0 q a ln d 1 2 upon r, d 1 2 is nothing but d a b upon r, right. Then q b, this q b ln r upon d 1 2, right, and plus q c, this is the q c ln, right, d 2 3 divided by d 3 1, right. The b, that because you want to find out the potential, that is your V A to B, right. If you recall that voltage 1 to 2, that d 2 upon d 1, that very fast diagram, that C 1 to calculation, V 1 to calculation. So, if you think that way, that means it is your from here to here it will be d 2 3 and then d 3 1, right. I hope you are understanding this, right. So, similarly for the second transposition cycle, I mean this one you make this configuration and this configuration of your own, because inductance we have seen it, right. Therefore, for the second transposition cycle it will be V A B, this is for this 2 means this is that second transposition cycle, this is the first transposition cycle section 1 is equal to 1 upon 2 pi epsilon 0, right. Then q a ln d 2 3 upon r plus q b ln r upon d 2 3 plus q c ln d 3 1 upon d 1 2. This is equation 14, right. Then for the third transposition cycle, that is V A B, this third transposition cycle 3 is equal to 1 upon 2 pi epsilon 0 q a ln d 3 1 upon r plus q b ln r upon d 3 1 plus q c ln d 1 2 upon d 2 3. This is equation 15. From your imagination also you can write this equation in without looking into the diagram also. If you understood, then no need to look at the diagram, from an intuition you can write it, right. Therefore, three different transposition cycle we got V A B for section 1, V A B for section 2 and V A B for section 3. Now, you take the average value of V A B, right. So, the average value of V A B means V A B is equal to 1/3 V A B for first transposition cycle plus V A B the second transposition cycle plus V C V or A B V A B for the third transposition cycle, right. You substitute all and then simplify, you will get this step, you please do it. I am right, I have made this one final one, that 1 upon 2 pi epsilon 0 q a ln, it will be d 1 2 d 2 3 d 3 1 to the your what you call to the power 1/3 divided by r plus q b ln r upon d 1 2 d 2 3 d 3 to the power your 1 by 3, right, cube root. Therefore, V A B is equal to 1 upon 2 pi epsilon 0 q a ln d e q upon r plus q b ln r upon d e q, where d e q is equal to d 1 2 d 2 3 d 3 1 to the power 1/3, that is cube root, is equal to, I am writing here capital D A B into D B C into D C A 1/3. This is equation 17, right. So, this is average value of V A B, right. Similarly, this is an exercise for you, because I have done for you V A B, right. Similarly, average value of V A C from the inspection you can write, V A C will be 1 upon 2 pi epsilon 0. Look, here it is V A B, Q A and Q B, right. So, Q C will be eliminated automatically when you will substitute, no, Q C will automatically eliminated and V A B will be in terms of Q A and Q B. So, here also from your intuition you can write V A C will be 1 upon 2 pi epsilon 0, it will be Q A ln d q upon r d q upon r plus Q C ln r upon d q, this is 18. So, straightforward you can write. After this you add equation 16 and 18, that means V A B plus V A C, these two you add. If you add, it will be 1 upon 2 pi epsilon 0, please add of your this thing, it will be 2 q a ln d q upon r plus q b plus q c into ln upon r d q, this is equation 19. But we know that q a plus q b plus q c is equal to 0. Therefore, this your from equation 12, therefore, q b plus q c is equal to minus q a. So, equation 12 it was q a plus q b plus q c is equal to 0. Therefore, q b plus q c is equal to minus q. You substitute here, right, in the equation 19 you substitute here. If you do and simplify, just put it directly you can write, then it will become V a b plus V a c is equal to 3 q a upon 2 pi epsilon 0 ln in bracket d q upon r. This is equation 20, that means V a b plus V a c is equal to your 3 q a upon 2 pi epsilon 0 ln d q upon r. This is equation 20. I hope you have understood. No, things are simple, right. Therefore, after that you have to make it some mathematical phasor representation, because we have to calculate the capacitance, right. So, make it, this is V b c is a reference, this is V a V b c a, V b c, V a b and V c a, right. Now, this one you make it like this. If you make it like this, this is your V b c, this phasor is V b c, right, and this is V a b. So, from here I am drawing the triangle, that this is V a b, right, and this is V c a. So, drawing the triangle, arrow is downwards, V c a, that means this phasor you convert it to a triangle. This is a balanced system, not unbalanced, balanced system, right, and neutral will be here, right. So, if it is a neutral, so this tip actually, this is V a b, though this tip will be a, and this is V b c. So, this tip will be b, and this is V c a. So, this tip will be c. That means, for your understanding, this will be actually a, right, and this is V b c. So, this is b, and this is V c a, this is c, right. Therefore, and this is the neutral. So, this voltage tip is here, this voltage is V a n, this voltage is V b n, and this voltage is V c n, and this angle actually 30 degree, this angle 30 degree, and this angle 120 degree, right. But not writing here, then figure will become clumsy, but this is understandable, right. So, what I am doing, that what we are doing it, that this V p c is this reference. So, this is V a b, so this is V a b, and this is V c a. So, make V c a, that arrow direction will be same as it is, just triangular formation, and this is neutral, say, right. Therefore, phasor diagram for balanced 3-phase system. Now, from figure 6, that means from figure 6 you can write V a b is equal to V a n minus, now you do vector, this phasor also, V a b is equal to V a n minus V b n, that is your this V b b, the look, this V a b, the way you do the vector phasor, V a b is equal to this tip is here, means opposite. So, minus V b n plus V n, I am writing this one first, then this one, but if you take for your understanding I am telling this V a b is equal to V minus V b n, because arrow tip is here opposite. So, minus V b n, then this tip is here plus V a n. So, writing V a n first minus V b n, this is equation 21. I hope you have understood. Similarly, we want A B B C C A, first you see that V a c, right. So, in this case V a b plus V a c. So, V a c will be is equal to V a n minus V c n. So, let first see the V c a. V c a is equal to, it will be minus V a n, because V c a is equal to, the way you do the vector phasor also same thing, that phasor is a rotating vector, right. This is the difference between phasor and vector, right. So, your V c a is equal to minus V a n, writing first, plus V c n, right. Therefore, V c a is equal to V c n minus V a n, but if we write V a c, it will be just opposite, V a c will be then, so you just interchange that c and a, it will be V a n minus V c n, right. Therefore, V a c is equal to V a n minus V c n, this is equation 22. I hope this simple thing, but sometimes confusion arises. So, hope there should not be any confusion. I hope you have understood, right. Therefore, then from this phasor diagram, your V b, your what you call, from this phasor diagram here also V b n is equal to V a n minus angle 120 degree, right. So, this is your V a n, this is your V a n. So, V b n actually lagging from V a n lagging by 120 degree, because this angle is 120 degree, Therefore, VBN is equal to VAN angle minus 120 degree we are writing 23, understandable. Then VCN is equal to VAN from here to here, it is 240 degree, but lagging. So, VCN is equal to VAN angle minus 240 degree, this is equation 24. Hope this is no confusion, right, straightforward. This if this VAN, VBN is VBN is the reference, then VBN is equal to VAN angle minus 120 degree and VCN move this way by VAN angle minus 240 degree. This is equation 24, right. Therefore, adding equation 21 and 22 and these two equation you add, VBAB plus VEC, these two equation you add, right, and substituting VBN is equal to VAN angle minus 120 degree and VCN is equal to VAN angle minus 240 degree. You substitute and you add, substitute and simplify, this is your job, right. All these things we have discussed and explained, right, there should not be any confusion anywhere, right. Therefore, if you do so, VAB plus VAC actually is equal to 3 VAN, this is equation 25. This relationship you have to establish, that VAB plus VAC is equal to 3 VAN, this is 25. Now, from equation 20 and 25, that means this is 25 and this is equation your this is equation 20, this is the VAB, that is VAB plus VAC, this is equal to actually 3 VAN. Therefore, 3 QA by 2 pi epsilon 0 ln dEq upon r is equal to 3 VAN. So, 3 will be cancel both side, right, cancel both side. Therefore, you can write QA upon 2 pi epsilon 0 ln, right, and then dEq upon r is equal to VAN. This is equation 26, right. Therefore, capacitance, now directly you can use that. The capacitance per phase to neutral of the transmission line is then given by CAN is equal to QA upon VAN, Q, because Q is equal to CV, you know, in general. So, CAN is equal to QA upon VAN is equal to 2 pi epsilon 0 ln dEq upon r farad per meter. So, natural log you convert to this log, right, or you can get it CAN is equal to 0.0242 log dEq upon r microfarad per kilometer. This is equation 28, right. So, up to this things are explained, right. Therefore, for equilateral spacing, that is if we assume that equilateral spacing, the D12 is equal to D23 is equal to D31 is equal to D. Therefore, dEq also will be D, because D into D to the power 1/3 is equal to D. Therefore, CAN is equal to 0.0242 by log D upon R microfarad per kilometer. This is equation 29, right. Therefore, the line charging current the line charging current for a 3 phase transmission line, I in bracket I am writing line charging, same as before, j omega CAN VLN, ln VLN means line to neutral voltage. That means, if you have a phase ABC, that means it is either VAN or VBN or CN. In this case, we are using CAN. So, in this case, L will be equal to A VAN, line to neutral, but not writing, right, not writing, because your CAN, CBN, CCN for balancing all are same, but anyway, this is ampere per phase per kilometer. This is equation 30, right. Next one is bundle conductors. So, up to this charging current is required, later you will see, right, particularly for the your characteristic of transmission lines, then your this at that time we will see all the details, right, but this is necessary. Now, bundle conductors. So, bundle conductors we have seen for 2 conductors, 3 conductors and 4 conductors, right. So, it is 3, 2 already we have seen for inductance cases. So, here I am not giving you the diagram, the same diagram. So, geometric mean radius of the bundle conductor can be calculated earlier for the inductance calculation, with the exception that the radius r of each conductor is used, right. So, in that case, for bundle conductor case, for inductance we have used r dash, right, that is for calculation of internal inductance. Here no internal your capacitance. So, nothing is there, no internal capacitance is there. So, that is why we will use r only, but not r dash, right. Therefore, if d is the bundle spacing, then for 2 conductors arrangement, just imagine that 2 conductors, 3 conductors, 4 conductors we have taken, no. So, ds is equal to r d to the power half, right, the geometric mean radius for 2 conductor case. In the case of inductance it was actually r dash, but in the case of capacitance it is r. Go back to the diagram. Similarly, for 3 conductor arrangement, that is equilateral triangle, this diagram also shown for inductance cases, but in this case ds is r d square to the power 1/3. So, here no question of r dash again, only r. This is your 32, and for a 4 conductor, that is quadruplex arrangement, ds will be root 2 r into d cube, but in the case of inductance it was r dash. So, here it is no r dash to the power 1/4. This is equation 33, right. So, considering the line to be transposed, the capacitance per phase is given by, if you assume the line is a transposed line, right. So, these are the conductor arrangement is given, that if you have this kind of arrangement instead of A, B, C, right, this kind of arrangement you have. So, this equation, basically this equation, that log of d upon r, instead of this equation we can write, if we assume that considering the line to be transposed, the capacitance per phase is given by in general, right, this one, that CAN is equal to 0.0242 log dq upon ds microfarad per kilometer. This is equation 34. We are writing d upon r, that is for equilateral spacing, but if you have that kind of configuration, so generally we will write log dq upon ds microfarad per kilometer. This is equation 34. So, thank you.